Good. Okay, so good morning, everybody. So today we'll discuss a question going back to Bourgain, the slicing problem. So as it happened in the 80s, Bourgain studied the maximal function operator, which is associated with an arbitrary convex body, and he proved L2 boundness with bound which was dimension free just by some universal constant. And this led him to study other questions, and particularly the following questions I'm describing now, which looks like more innocent in a way. So that's the question. So let K in Rn be a convex body of volume 1. And the question is, does there exist a hyperplane H, codimension 1, such that if I look at the intersection of K and H, the volume of the intersection is at least 1 over 10, or in general, at least a universal constant. Okay, so that's the question. And Bourgain in 1984, in his paper, he wrote that at the time of the writing, he doesn't know the answer. But subsequently, he published some bounds on it. So in 91, and he got, in place of a constant here, you can put something slightly worse, into the minus 1/4 over log n. So this is what he proved in what he published in 91. Maybe he knew it a bit earlier because there are some references earlier to this result. Another proof in 2002, and his proof used K convexity and the sub-Gaussian processes, comparison with some processes. This is one proof. Then, well, there was not big progress, so the log factor was removed in 2006. But the proof was different. It used the Laplace transform. We'll see today how you work with the Laplace transform and get more. So these are two different proofs of this more or less the same bound. Good. Then Lehec and Pala used stochastic equalization and get another proof, n minus quarter. So this was, I think, in Vempala 16. Okay. Well, so you had three different proofs, looked rather different, of the same n to the 1/4 bound. So some people thought that it could be correct. In fact, you could think that you could find some counterexample. Maybe, I don't know, look at the space of matrices, right, in some convex set of matrices in dimension n square. And then you need to prove some root of n bound, because the fourth root of n square is root n, and root n is a prevalence scale in random matrix theory. But no, there was no counterexample. So the story was not closed, and apparently Yuan Zi Chen, in the end of 2020, or 20, I think I know 2020, so he got something much, much better. So this was kind of a surprise. So he got so e to the minus root log n log log n, which is, so if you, I mean, this is n to the minus little o of 1, so it's better than any polynomial. And his proof used, again, stochastic equalization, but his analysis was a bit more intricate. So somehow, in some sense, I would say that some people thought it's the end of the story, but maybe it was just some kind of psychological block. And after Chen, it was clear that I mean, yeah, this question can go much further in this problem. And then the estimates were improved later. So with Lehec 22, I think we got log n to the 1 minus 4. And today we know 1 over root log n, and this is what we'll prove today. Okay, so this is the history of this slicing problem. Okay, so let me begin by some questions about some study of sections, hyperplane sections of convex body. So I'll begin with Henri. So Henri was actually before Bourgain. So Henri was, I think, 1980. And the extension to non-symmetric sets is rather easy. So suppose that you have a convex set in Rn. Say X is uniformly distributed in K. And let's assume that it is centered. And assume that the Barrett center of X lies at the origin. And the covariance matrix of X is a scalar matrix. Okay, so this, as we said, I think, sometime this week, whenever you have any convex body, body means compact, so finite volume, non-zero and finite volume. Whenever you have any convex body, you can apply some affine transformation and make the covariance matrix a scalar matrix. So this is just choosing the right position. And the nice thing about this condition is that it gives quite strong regularity property for volumes of hyperplane sections. So the conclusion is that for any hyperplanes H1 and H2 passing through 0 in Rn, if I look at the volume of one section, so the ratio, I mean, it's mostly universally constant times the other section. And in fact, I even remember the value of, I think the best value found by Fadeli is square root of 6. So, so we know that if you have any convex set, which is centered, and you normalize so that its covariance is a scalar matrix, you know that the volumes of all sections through the Barrett center are the same. Okay, so somehow we know that all sections are the same, but we don't know what is this common value. So this slicing problem is still unsolved, although we know that they're all the same. Okay, so let's prove this theorem. Any questions? Please say something, ask something. Yes, please.
Is there some versions for like lower dimensional subspaces?
Yes. So if it's codimension K, you'd expect C to the K. C to the codimension. That's the, yeah.
So this is a conjecture or question?
I mean, the case K equals 1 is already open. But, I mean, if you, so by induction, if you know it for K equals 1, you can do that, and you can get it C to the K, right? If it's true for 1, then that's the, so it's equivalent to the original conjecture, yeah. More questions? Okay, so let me prove this theorem. Okay, so let's fix some unit vector theta. And let's look at the random variable x times theta. Okay. So its density, what is its density? So if this is K, you just need to, so if this is K, and this is theta, then its density at T, or theta, say at T, is going to be what? So you look at, this is T, so you look at the section orthogonal to T, and you look at its volume, right? So the rho theta of t is the volume of the section t theta plus t plus theta perp. So this is a hyperplane over the volume of K, because the total volume is not normalized to 1. Okay, so this is the density. Now, well, I should use the... Okay, let me try to stop it in the middle. Right, that's, I think, yeah? Okay, so we know that the covariance matrix of X is a scalar matrix. So let's write it as sigma square times identity. That's the definition of sigma. Okay, and it is centered. The random variable x times theta over sigma is isotropic. Okay, so it has mean 0 and variance 1. Moreover, if I look at this density, so we have this density, which was the volume of the sections. So this function, by Bourgain-Minkowski, it is log concave, right? Because this is actually Brun's principle, maybe even before Bourgain-Minkowski. So if you have two... Oh, sorry. Thank you. So the density is log concave. By Bourgain-Minkowski, right? Because if you look at two sections, at T1 and T2, by convexity, the section in the middle, T1 plus T2 over 2, it contains the Minkowski average of these two sections, so the volume here would be larger than the geometric average of these two volumes, so we get that it is log concave, okay? Actually, I think that this is the first time in this week that we see the Bourgain-Minkowski inequality, which is a bit, well, it means that something is somewhat wrong in the, so we have Cauchy-Schwarz like 15 times, but Bourgain-Minkowski almost never. So maybe we miss something fundamental in this business. Because it should be like something used all the time. Okay, so it's log concave by the Bourgain-Minkowski inequality. Now, what is the density of x times theta over sigma is what? So it's rho of theta. So we need to scale it by sigma. So if you divide by sigma, you need to multiply because it's in the other direction. So that's the density of this random variable. Okay. So this is, as we said, this is isotropic log concave density. In 1D. So we know that it is bounded by exponential, and so we know that it's bounded by two things. So it is somewhat. So it's like this, right? It passes. Let me put it in orange. So it passes between these two things. So we know that for any t in R, sigma or theta of sigma t is between some constant e to the minus t and c, and c tilde, the indicator function, where t is smaller than c hat, let's say. So for some universal constant. So in particular, if I put here 0, then sigma rho theta of 0, or rho theta of 0 is between c2 over sigma and c1 over sigma, which means that the volume of the sections is in band of theta, right? So this is for any theta. So the volume of the two sections, the ratio. Okay, so this is rho theta 1 at 0, right, times the volume of K. So this over this is bounded by two constants, right? And this is the rho theta 2 of 0 times the volume of K. So it is bounded by C2 and C1. C tilde and C tilde. Okay, and the fact that it's root of 6 requires more delicate analysis of one-dimensional distributions. Okay, so this is nice result, going back to Hensley in the symmetric case. And there are a few conclusions from the proof. Okay, so first, what we see from this discussion is that if I would take another slice of K parallel to theta perp, okay, then I get another value of the density. But because this bound, we know basically that the value at 0 is sort of the maximum, okay? So what we learn from that is that the central section, so the hyperplane section through the origin, through the barycenter, let's say, it's better to say, through centroid, barycenter, is up to up to a universal constant, multiplicative universal constant, the maximal one among all parallel sections. The maximal among all parallel hyperplane sections. Okay, so if you study the slicing problem, you can restrict your attention to sections through the barycenter, because sections through the barycenter up to a factor of E, Mattia, I think E, no? Yeah, up to a factor of E, they are the largest ones. Okay, so if you look to lose a factor of E, then you only look at sections through the barycenter. And another thing is that if K is centered, then you can relate, we see from the proof that the volume of the section times the variance. So let's say K is centered. Let's say volume of K is 1. And let's say that X is uniform in K. Then we get that the volume of the central section times the L2 norm of X in the orthogonal direction. Okay, so this is the section. And this is the variance, the standard deviation. This is roughly 1. So this notation was used by Joseph. No, you had 2 tildes maybe. 2 tilde. Okay. I usually put just 1, but I put 2 for you. Okay, so this 2 tilde, this means that the ratio, okay, so I write that A roughly B, this means that A over B is between two universal constants, positive universal constants, okay? So where these are absolute constant. Okay, so we get that it is roughly 1. Actually, in general, without volume K, we could say that it's the volume of K, what's written here. So we can relate the volume of the section to the L2 norm of linear functionals. So in particular, what we get is that, okay, now we should put both up. Yes, this was the trick. So the third conclusion is that, so if the volume of K is 1, and the volume is 1, then what would be the supremum over all hyperplanes of the volume of the section? So we know that this is the supremum of 1 over x theta square, where theta is in unit vector. That's what we said. And this actually maybe equals. This equals, I think, the operator norm of the inverse covariance matrix. Yeah, because it's inside, it will be minimum. So it's yeah. Okay. So in some sense, what you this brings us to the question that when you study slicing problem, you may forget about hyperplane sections and just look at the relation between volume and covariance. So the question is basically what control over the operator norm of the inverse covariance matrix you can get under the assumption that the volume of K is 1. So for now on, we will not discuss so much hyperplane sections, but we'll discuss covariance versus volume. And this is embodied in the isotropic constant, so it measures basically covariance versus, so you can say volume, but let me write entropy. You could say that log of the volume of a convex set is the entropy, the differential entropy of the random vector distributed uniformly in K. So this is the point of view that we like to take here. So there are two ways to measure the size of a convex set. One of them is its volume or its entropy, how much space it occupies. And the other is the covariance matrix. So how large is the covariance matrix? And the slicing problem asks about the relation between these two numbers. So the volume versus the covariance. Okay, so we define the following. So for K in Rn convex, its isotropic constant is Lk. So this is Bourgain's notation. Hensley used V, but it's stuck. I think you are used to Bourgain's notation. So the determinant of the covariance matrix of K, of the uniform measure on K, I should not write it, over the square of the volume of K to power 1 over 2n. Okay, so this is the isotropic constant of a convex set K. I will explain why this is the right way to normalize these two things. But I mean, you can think for yourself, it's a fine invariant. Okay, why entropy? And if you have an absolutely continuous log concave random vector in Rn, so more generally, you can define its isotropic constant Lx to be something similar. So you look at the covariance, and you should divide, apparently, by e to the twice the entropy of x, where the differential entropy of x, so where the entropy of x is minus rho log rho, where rho is the density of x. Okay, so these are the isotropic constants, and this is what we want to study when we discuss hyperplane sections. So what we get from this definition, so if so suppose that the volume of K is 1, so just some comments. So if the volume of K is 1, then Lk is just the determinant of the covariance matrix to power 1 over 2n. Okay, this is an n by n matrix, and you take its power 1 over 2n. So what you get is that it cannot be, so you know that it's the operator norm of its inverse is it must be at least, so the minimal eigenvalue must be at most the geometric average of the eigenvalues of this matrix. And what you get is that there exists a hyperplane section by what we wrote above. such that the volume of the section is at least LK. Right, this is just because the minimal eigenvalue of, the minimum of theta of the covariance of x theta theta, which is this is at most the determinant to some power. And if you know that and if furthermore you know that the covariance matrix is scalar, then for any h through the barycenter, the volume of the section is 1 over LK. Okay, so we're in the situation, you know that all sections have volume 1 over LK, and you don't know what is this common value. Okay, questions about this isotropic constant, the definition? Maybe let's say a few of its properties. No questions? Okay. By the way, so about this entropy, I should say a few things. So it's not completely canonical, so you could see for convex body, no, as all constant is something completely standard. Nobody argues what it is. But for all concave, you can see in the literature several definitions. Okay, so I just want to remark that in the low concave case, so in the low concave, in the definition of Lx, so we may replace entropy by something else. So we may replace entropy by other things. By, for example, okay, so entropy, what the entropy is the entropy of x. This is the expectation of psi of x, if rho is e to the minus psi. But you may replace it, you may replace the entropy by something else. So in place of looking at the expectation of psi of x, you may look at psi at the barycenter. So nothing, it will only change by universal constant. As if psi is constant, or by the infimum of psi, or by things which are even more dramatic, like you can take anything which looks like, I don't know, you can take e to the psi over 2, and then take twice the log of that. So all of these things, this would only change change Lx by multiplicative by universal constant. So and since we in this slicing problem only care about that, then this doesn't really matter. But you can see in the literature, I think this is even more popular things than just the entropy. And let me just explain to you why these things are close enough. So there is a nice lemma with low concave games. So the claim is that for any low concave random vector, okay, so if x is low concave in Rn, density is e to minus psi, then you can say that the psi at the barycenter is at most the entropy. Okay, that's just Jensen. And this is at most the infimum of psi plus n, and exactly this plus n is exactly what it means that you get the same as isotropic concept to a constant. Or you can say that if you look at, if you take any power of psi of exponential x, any power smaller than 1, if you take power 1, it's infinite. But if you take any power smaller than 1, then this is at most the infimum of psi plus some constant, maybe plus n, maybe a bit better than that. So that just explained, and this, yeah, this lemma shows that, so let me remind you that the isotropic constant is, So let me just write here. The isotropy constant was the determinant of the covariance over e to the twice entropy. So it means that if you change, yes. Thank you. Yes, yes, yes. Yes. So if you, yeah, everything, like if psi was constant, everything was trivial. This is kind of the, okay. But yeah, so if you see, you can see that if you, any quantity that differs from the entropy of x by O of n, you can put it here, and these quantities do differ by O of n, and you get the same isotropy constant up to some immaterial factor. Okay, so let's prove this lemma. It's a short one. So yeah, so we said that the entropy. So first of all, yeah. So psi at the centroid by Jensen is smaller than e to the psi of x. Yeah, I learned these tricks from this is just Jensen. I learned these tricks from several people, from paper by Spingran and from Mathieu Ferdelizy and Bob Kov, in Latava also. Okay, so this is just Jensen. Now, there is a nice thing. So if you take any y in Rn, a convex function lies above its gradient. So if I take, this is the point x and this is y, I know that psi of y is larger than psi of x plus grad psi x y minus x. Okay? And let me also assume that the density assumes that the density is continuous. It's not a big deal. So I can write that psi of x is at most what? It's at most psi of y minus grad psi of x y minus x. Okay? And this thing, so what is this? So this is psi of y, okay, minus grad psi y, minus the integral of grad psi x y e to the minus psi, which will be 0, I claim, plus the integral of grad psi x x e to the minus psi x, which equals n, I claim. This equals n. Okay, so this equals 0, I mean, just the integration by parts. So if psi always continues, it means that this function e to minus psi goes to 0 to infinity. What's written here is del y, maybe minus del y of e to the minus psi. So the integral of the derivative is 0. And here this is the same. So this is, okay, integration by parts, you see that this is the sum of del I psi xi. If you get by parts, you get del I e to the minus psi. So we write this as del I e to the minus psi times xi. With the minus sign, you integrate by parts, you get n times 1, so you get n in total. So this proves the first part. And the second part is also very short. So it just says that, again, for any y. So this expectation, so this is the integral of e to the minus psi x over 2 dx, because the density is e to the psi, minus psi. So this is like e to the minus psi y outside. You take the infimum over y and you get, so yeah, you take, this is true for any y, so if you take the infimum over y, you get psi of, the infimum of psi plus n. For the second thing, you do this trick, so you take outside psi of y over 2, and here you write e to the minus psi of x plus psi of y over 2 dx. And now you use again the convexity of psi, so this will be at most e to the minus psi x plus y over 2, right, because it's a convex function. Well, what? Olivier, what? Okay, so just continue. So this thing, you just change variables. This equals what? So you change variables. Y is just constant, so it's x over 2. So you dx over 2 you need, so you need 2 to the n. This equals 2 to the n. So you get 2 to the n e to the minus psi of phi and infimum over y. Okay. So if you take the psi. This is minus, yeah. There was minus, yes, thanks. Yeah. Okay, is something wrong still? No, it's okay. Good. Now, okay. So this is why local functions are very stable objects. All right. So they are rather stable objects. And there are many ways to define the entropy constant. The entropy is something very profound in the low concave business. Okay, now, what else should I tell you about the entropy constant? Okay, so properties of entropy constant. A finite variant for any t affine linear. Invertible, actually. Important to say invertible, otherwise you would solve the sizing problem. Yeah, invertible. Okay. It's if x is a random vector with two components, let's say in R2n. So this is an Rn, Rn. They are independent. Then what is the new isotropy constant? It is the geometric average of these two guys. Okay, so it's a the logarithm is subadditive, so this the infinity is the infimum. It is minimal, so it is always at least 1 over root of 2 pi e. Okay, 2 pi e because the ball of root n has volume roughly 1 over root of 2 pi e to the n. Yeah, okay. It's at least 1 over 2 pi e with equality for the Gaussian. For Gaussians. So why is it true? This is because it's well known that if you want to maximize the entropy for fixed variance, then you take the Gaussian. Because, so among all random vectors, of a fixed covariance, entropy is maximal for Gaussians. This is like one-line proof. So you enough to prove a dimension 1, because, okay, so if you can dimension 1, and if gamma is the Gaussian density, just write that, just use the fact that rho log of gamma over rho is at most rho gamma over rho minus 1, because log of x is most x minus 1, and this is 0. And okay, this is something very simple from using just, I mean, it follows from this inequality. It's that the entropy in dimension 1, and by some translation you get it in all dimensions. So the question, so the slicing problem is equivalent to the question Is it true that Lk is at most, so it is you know it's above some universal constant, this we know. And the question is whether it's true that it is smaller than some universal constant for any n and for any k in Rn. So that is the question. If it's true, then it means that in the local wave category or in the convex body category, entropy in terms of covariance describe the same quantity. And we saw that there are many things that describe entropy, and if it's true, then also covariance. You could add it to these things, but okay, this is still a bit open. Okay, and some examples. I think I numbered these things, so this should be number 4. So what do you get for the cube? For the cube, I remember because it's 1 over root of 12, because it's the variance of a uniform random variable. And for the simplex, I don't care which simplex because it's all affine invariant. I don't remember, but it's roughly 1 over e. Okay? When I put 2 tildes, I mean it means that this equals this plus little o of 1 as n goes to infinity. Okay, now this last problem, okay, it has quite a few recurrent formulations. Yes, what's the question?
Is there some expression of this isotropic constant in like geometric quantities of the...
Yes, many expressions, many.
What? If it's smooth, for instance, the convex body in curvatures.
What?
If the convex body is smooth, can you express it in curvatures?
You can, any integral on the convex body, it's an integral of two homogeneous functions. Okay, so the volume is an integral on the boundaries. There are many ways to express the integral, and you can also express the integral of x squared on the boundary. I don't know if it's super useful, but yes, you can do that. Or you can use the surface area measure on the sphere via the Gauss map and transform the integrals to the. So I mean, if the volume of k is 1, so basically you need to compute these integrals and it is determinant. So that's the isotropic constant determinant of these integrals, k and centered. This is what you need to compute, and you can transform these integrals in many ways. Okay, this is a bit simple. If you want, maybe you'd like the following. So if you take a random simplex, okay, maybe one possibility is to say the following thing. So if x1 up to xn plus 1 in ki IAD uniform, okay, then and k, let's say k is volume 1, just to normalize. So you can look at the expectation of the volume of the convex hull. So this is a simplex. And let's put a square. And this equals Lk to some power times some, so this is Lk to some power n or 2n, square 2n, times some dimensional coefficient. So that's another way, maybe it's more geometric to compute the isotropic constant. So there are quite a few equivalent formulation of this thing. So I don't know, volume of sections is geometric. Think a bit. Yes. So let me just formulate. Okay. Let me formulate. Oh. Yes. Let me formulate some other consequence of recurrent formulations. Maybe some of them will be geometric. Okay, maybe I have ones that you might like. So, okay, an recurrent formulation. So this will be item. This was 4, maybe. So 5. So recurrent formulation. Which I think is geometric, of slicing. Okay, so suppose that K is a convex body of volume 1. You know what? Not a volume 1. Let me know. Be a convex body. Can you find an ellipsoid does there exist an ellipsoid E of the same volume such that if I look at K intersection with a slightly enlarged ellipsoid, so I dilate it by universal constant, should be at least 1/2 of the total volume. Where C is universal constant. Okay, so this is exercise that, I mean, this follows from reverse order inequalities for quadratic forms. So prove the equivalence using reverse order inequalities for quadratic polynomials. Okay, so what do we have here? We have some convex set, and we ask if you can find some ellipsoid of the same volumes. After you scale it a bit up, it captures half of the mass. Okay, and this ellipsoid is related to, the best ellipsoid would be related to the covariance structure. Okay, maybe I won't solve this exercise. It's not so difficult, but yeah. Okay, this ellipsoid is about the covariance structure, and if it captures a lot, then you have something about some information about the covariance matrix. And let me say what is known here. Actually, what is known, some things are known. So there is something called the Miller ellipsoid, which is a weak version of this conjecture, but it is a theorem. So it is known that there is a so it is known that Millman's theorem from the 80s states that for any convex set K in Rn, there exists some such ellipsoid of the same volume such that if you take the intersection, actually I don't need to scale. I leave it this way. It is at least C to the n for universal constant C. Times the volume of K. For universal constant C. Okay, so this is already, okay, this is much weaker here. Here we don't want 2 to minus n, we want half. But this is already enough for many things. So this is enough to prove, for example, Bourgain and Millman, or quotient of subspace theorem, or reverse Bourgain-Minkowski, or some other things from the, or quotient of subspace, reverse Bourgain-Minkowski. So there is some theory around this Millman ellipsoid, which is very nice. And in some sense, the slicing problem is a refined conjecture of this theory of the Millman ellipsoid. Okay, maybe I should only say what is the Bourgain-Millman inequality. Bourgain-Millman is the inequality that for any convex body K in Rn, it's polar, I'm sure everybody knows. Let's say 0 is inside, otherwise, okay. The polar is, otherwise, the polar is non-compact. So it's the set of all points where the scalar point is at most 1. And the Bourgain inequality states that the volume of K times the polar is at least okay, C over n to the n. And this is up to C to, this is optimal up to C to the n. So up to exponential factoring, so we kind of understand volumes very well already up to exponential factors in dimension. This is known from the 80s. And slicing wants to understand them in a better way, in a more accurate way. Okay. Maybe so it is conceivable that this thinking of up to universal constant is completely wrong in this business. So it's not clear that you should study this problem in the usual way you study things in high-dimensional geometry, where you say, okay, up to a constant, it's okay, but and the precise values are not entirely relevant. So let me just tell you two implications. So two conditional statements. So the first one is that, so as far as we know, it could be that the supremum of the isotropic constant over all centrally symmetric convex bodies in Rn, it could be that this is attained for the cube. We know no example where it's above the cube. So, but if this is true, then Minkowski lattice conjecture follows. So this appears in the paper of Magazinov explicitly, in 18 or something. What's the Minkowski lattice conjecture? This is the conjecture that for any lattice L of covolume 1, of determinant 1, so that's the fundamental, then, and for any translate, and for any translate, so if you intersect L plus X, if you take it lattice and intersect it with some shape like this, so the shape of all points in Rn, where the geometric average of the points, so this comes from algebraic number theory. You see such product if the lattice corresponds to a number field. Okay, so the conjecture that this is non-zero. So there is some, anyway you remove the lattice, you intersect this thing. And when Minkowski proved in dimension 2 in the very early 20th century, and it's known today up to dimension 6, 7, 8, some number, but it's open in general, but it would follow from this slicing. And another result is that, this is about the symmetric case. In the general case, you conjecture that supreme should be attained for the simplex. Maybe there is some geometric argument. Actually, it's not completely unlikely. There is some geometric argument you completely miss that solve it exactly on the nose, and you get that the supremum over all convex sets is attained for the simplex. This is known in dimension 2, for instance. If this is true, then Mahler's conjecture follows. Non-symmetric Mahler. So Mahler wrote two papers, one on the symmetric, one on the non-symmetric. So the Mahler conjecture is a refined version of Bourgain-Millman, and the conjecture is that the volume of K times the polar is minimized for the simplex. So put a square. The simplex is kind of self-dual if you center it. At least the dual is isometric to it. Okay, and this was proven in 2 dimensions by Mahler in the 1930s. In the 30s. Okay, very good. Now, I want to discuss this root log n bound. Okay, so this is just background on the isotropic constant. Now let's discuss the best known result, which we have today, which is the slicing is correct up to root log n. Okay, so why is Lk smaller than root log n? That's what we want to know. Okay, and this will be related to KLS and to thin shell and the Poincaré constant. So we begin by defining, this is a small variant of a definition of Joseph from yesterday. He put S and I put sigma n. So maybe sigma is in Greek and S is in Latin, but it is the same letter. I'm not sure. I think so. So let's write the supremum over all isotropic local random vectors in Rn. And I look at the supremum of the variance of x squared, okay, and divide by n. Let me divide it by n. And this is sigma n squared, okay. And the claim is that so I claim that it's pretty much the Sn from yesterday by reversible inequalities. I claim that the variance of x squared over n is roughly the variance of the Euclidean norm of x, which was defined yesterday. So this means that, so if I have my convex set K, we recall that we have this thin shell phenomena, that most of the mass is located in a thin spherical shell centered at the origin. Okay, so most of the mass is in this region. So sigma n is the width of this region. Okay, so this is the width here. So the radius is roughly root of n, if you are isotropic, and sigma n is the width of this thin shell that captures everything. Maybe I should explain. So why is this true? This equivalence, let me quickly. So the variance of x squared is the expectation of x squared minus n squared, because you are isotropic, you know that this is square, which equals x minus root of n, x plus root of n, and this is at least n times x minus root of n squared, which is larger than n times the variance of x. And for the other direction, I mean, if you know that, okay, if you know that this set has large measure, let me put 3. So this set is large. You know that typically x is between these two things. This implies that x, and e is roughly root of n. This implies that x squared with probability 3/4 or something is at most, so I can put the root of n. We know that this is. So this implies that x squared would be between n plus 3 root of n sigma n and something like so n minus 3 sigma n root of n. So this implies that the median, so the median of x squared minus n is smaller than the median of this thing is smaller than root of the variance of x times root of n. Okay, and this shows that these two things are equivalent. Okay, so we have this sigma n, and what we want to prove, and of course sigma n is smaller than the Poincaré constant. Let me X here. So sigma n, okay, so for some x, sigma n is, so if I look at the variance of x squared over n, this by Poincaré, it is smaller than 1 over n times Cp of x times the expectation of the gradient of this function. If this is f of x, its gradient is, as Joseph said yesterday, it's 2x. So I get 2x squared, which will be 4 Cp of x. So what we get is that sigma of n square is smaller than at least 4 times the supremum of the Poincaré constant of x, where x is tropical or concave. which is at most for log n by constant log n by what we saw yesterday. So whatever remains to prove the boundary isotropic constant is my theorem with Eldan from 2011 that for any k in Rn, the isotropic constant of k is at most C sigma n, where C is a universal constant. And this is what we'll prove after the break. Okay, so now 10 minutes break.